Transitive relation means if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. That is called as a transitive relation. If no element of A is related to any element of A, that is R is called a empty relation denoted as R is equal to a null set which is a subset of A class A. Suppose if a set A satisfies all these three relations, that is reflexive, symmetric and transitive, such a relation is called an equivalence relation. Hello dear students, welcome to this session of Discrete Mathematics Revision class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. Now today in this session I am going to discuss regarding relations and the functions. Very important. You will get one full question from this for 15 marks from this session. So let us know regarding first relation. So what is a relation and the types of relations? So in the examination they may ask define a relation and write the types, or define a relation and define different types of relations. Now let us know regarding relation first. So a relation is nothing but the subset of the Cartesian product A cross B. If A and B are any two non-empty sets, then A cross B is called the Cartesian product. Then the subset of this A cross B is called a relation. So A cross B subset is called the relation. So a relation R from a set A to set B is the subset of the Cartesian product A into B obtained by describing a relationship between the first element X and the second element Y of the ordered pairs A comma B, A into B. That is, so A into B is nothing but a relation. Let us take for example, if A is equal to 1, 2 and 3, B is equal to 3, 4 and 5. Now let us write a relation R is equal to X comma Y such that X plus Y is less than 5. Now what is the relation we are going to get? Therefore the elements of the set R is equal to, now just write down the Cartesian product of A and B is A cross B is equal to 1 comma 3, then 1 comma 4, then 1 comma 5. Right, that is a relation between the first element X and the second element Y of the ordered pairs. Now similarly take 2 comma 3, then 2 comma 4 and 2 comma 5. Then next 3 comma 3, then 3 comma 4 and 3 comma 5. So this is the Cartesian product. Now what is the relation given? The relation is a subset of A cross B. What is the condition? X plus Y is less than 2. Sum of the two elements is less than 2. So you can take 1 plus 3 is less than 5. 1 comma 3. Again 1 plus 4 that is equal to 5. We cannot take. 1 plus 5 it is 6. We cannot take. 2 plus 3 it is 5. We cannot take. 2 comma 4 6 2 comma, so we can't take. So only one element we will going to get. So R is equal to 1 comma 3 is the subset of A cross B. Therefore this is the relation which satisfies the condition X comma Y is less such that X plus Y is less than 5. Okay, this is an example for a relation. So that means a relation is a subset of the Cartesian product A cross B. Now what are the types of relation? This is very important concept. So you may expect this for 7 or 8 marks. Types of relation. So an empty relation. Empty relation means, suppose if a set contains no element, if no element of A is related to any element of a set. Let me explain. Empty relation means, if no element of A is related, to any element of A, then R is called the empty relation, denoted as R is equal to a null set. Empty is a subset of A cross A. The relation R in a set A is called an empty relation. So if no element of A is related to any element of A, that is R is called a empty relation, denoted as R is equal to a null set which is a subset of A cross A. Now, universal relation. What is this universal relation? If each element of A is related to every element of A, that is R is equal to A cross A, then the relation R is said to be an universal relation. That means if each element of A is related to every element of A, each element is related to every element of the set A, then the relation R is equal to A cross A is called an universal relation. So, both empty relation and universal relations are sometimes called as the trivial relations. They are called as trivial relation. Now, the third one, reflexive. This is very important. Reflexive, symmetric and transitive. So, a relation R on a set, A is said to be reflexive if A comma A belongs to R for all A belongs to A. That is, if A is related to A is true. If A comma A belongs to R, then it is called a reflexive relation. Reflexive relation. Second one, symmetric relation. So, a relation R on a set A is said to be symmetric if A comma B belongs to R implies B comma A also belongs to R for all A comma B belongs to A. If A comma B belongs to R implies B comma A also belongs to R, then it is called as a symmetric relation. The third one, transitive relation. Transitive relation means if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R for all A comma B comma C belongs to the set A. So, if A comma B belongs to R and B comma C belongs to R, this implies A and C also belongs to R, then this is called a transitive relation. Then it is called as a transitive. So, reflexive means if A comma A belongs to R, then it is reflexive. Symmetric relation means if A comma B belongs to R implies B comma A also belongs to R. Transitive relation means if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. That is called as a transitive relation. So, reflexive, A is related to A. Symmetric, A is related to B implies B is related to A. And transitive means if A is related to B and B is related to C implies A is also related to C. So, then such a relation is called transitive. So, reflexive, symmetric and transitive. Now, suppose if a set A satisfies all these three relations, that is reflexive, symmetric and transitive, such a relation is called an equivalence relation. So, in the examination they may ask define equivalence relation. So, what is the definition of an equivalence relation? A relation R on a set A is equivalence relation if R is reflexive, symmetric and transitive. If R is reflexive, symmetric and transitive. A relation R on a set A is said to be equivalence relation if R is reflexive, symmetric and transitive. What is reflexive? A comma A belongs to R. What is symmetric? A comma B belongs to R implies B comma A belongs to R. What is transitive? A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. So, this is an equivalence relation. Very, very important for the point of examination. Reflexive, symmetric and transitive, such a relation is called an equivalence relation. So, in general, types of relations are empty relation which contains no element and no element of A is related to any element of A, denoted as R is equal to null set subset of A cross A. Universal relation means if every element of A is related to every element of A, that is called a universal relation. And the third one is reflexive relation means A comma A belongs to R. Symmetric relation means if A comma B belongs to R and B comma A also belongs to R. Transitive means A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. If a relation R on a set A is reflexive, symmetric and transitive, then it is called an equivalence relation. Okay. Now, let us know regarding a function. So, definition of a function. A relation F from a set A to set B is said to be a function if every element of a set has one and only one image in set B. That means if there is a unique association from set A to set B. Let us consider these are two sets A 1, 2, 3, 4, A, B, C, D. So, if a function F from A to B is said to be a function, if there is an unique association, every element of a set has one and only one image in the set B. Now let us write 1 to B, 2 to C, 4 to A and 3 to D. So here the image of A is 4, B is 2, B is 1, C is 2 and D. So every element of A is associated with the elements of set B by unique time. Then such a relation is called as a function. So here the relation R is nothing but 1 comma B, 1 comma B, again 2 comma C, then 3 comma D and 4 comma A. So this is an example for a function. This relation is a function. Now next, different types of functions. So what are the types of functions? There are different types of functions. One function, onto function. Now one function, this is very important concept again. A function f from x comma y is defined to be a one or an injective function. One function, or it is also called as a injective function. Injective function. So if the images of distinct element of x under f are distinct images of x under f are distant, that is, for every x1 comma x2 belongs to x, f of x1 is equal to f of x2 implies x1 is equal to x2. F of x1 is equal to f of x2 implies x1 is equal to x2. Then such a function is called an one function, or it is also called as an injective function. Otherwise f is called many one function. So a function f of f from x to y is defined to be one or injective function if the images of distinct element of x under f are distinct, that is, for every x1 comma x2 belongs to x, if f of x1 is equal to f of x2 implies x1 is equal to x2, then it is called one function. Otherwise it is called many one function. Now move on to the second one, onto function. This is also a very important function. A function f from x to y is said to be an onto function, or it is also called as a surjective function. It is called as a surjective function if every element of y is the image of some element of x under f. That means if every element of y is some image of some element of x under f, that is, for every y belongs to y, there exists an element x in x such that f of x is equal to y. This is very important condition. That is, for every element y belongs to y, there exists an element x in capital X such that f of x is equal to y. Such a function is called an onto function. So one function and onto function. Now the next one is a one and onto function. This is also called as a bijective function. Bijective function. Bijective function means a function which is both one and onto. A function f from x to y is said to be one and onto function if it is both one and onto. So that means a function is said to be a bijective function if it is both one and onto function. So these are different types of functions, a function and different types of functions. Okay. Now move on to the problems based on this. Now let us take first problem. This is very important type problem. A relation R in the set A is given by 1, 2, 3, 4 up to 14 is defined as R is equal to x comma y such that 3x minus y is equal to 0. Check whether R is an equivalence relation or not. So to verify equivalence relation, check whether it is R is reflexive, symmetric and transitive. If all these three conditions are satisfied, then it is an equivalence relation, or if it is not satisfied, then it is not an equivalence relation. Now first find out what is given here. 3x minus y is equal to 0 means therefore y is equal to 3x. So the elements x comma y can be written as x and y is equal to 3x. So therefore the elements of the set, so therefore the relation R is equal to of the form 1 comma 3 times x. So when x is equal to 1, y is equal to 3 into 1 is 3. When x is equal to 1, then 3x means 3 into 1 is equal to 3. When x is equal to 2, 3x means 3 into 2, that's equal to 6. When x is equal to 3, 3x means 3 into 3, that's equal to 9. When x is equal to 4, 3 into x means 3 into 4, that's equal to 12. When x is equal to 5, 3x means 3 into 5 is equal to 15 does not belongs to R. We cannot take this. So, therefore, the elements of the R are 1 comma 3, 2 comma 6, 3 comma 9 and 4 comma 12. That's all. So, you cannot take 15 because 15 does not belongs to the set A, does not belongs to A. So, here the last element is 14. So, therefore, the relation R is equal to 1 comma 3, 2 comma 6, 3 comma 9 and 4 comma 12. Now, verify one by one. Reflexive relation. Reflexive. So, R is not reflexive. R is not reflexive here. R is not reflexive. So, what is the reason? Because A comma A does not belongs to R. That means 1 comma 1, 2 comma 2, 3 comma 3. So, 1 comma 1 does not belongs to R. 2 comma 2, 3 comma, so does not belongs to R. Therefore, it is not reflexive. Second one, symmetric. Symmetric. So, R is not symmetric. R is not symmetric. What is the reason? Because R is not symmetric, because 1 comma 3 belongs to R implies 3 comma 1 does not belongs to R. So, 1 comma 3 belongs to R, but 3 comma 1 does not belong to R. Similarly, 2 comma 6 belongs to R, 6 comma 2 does not belong to R. 3 comma 9 is there, but 9 comma 3 does not belong to R. 4 comma 12 is there, 12 comma 4 does not belong to. So, therefore, R is not a symmetric. The third one, transitive property. Transitive. R is not transitive. R is not transitive because if you take 1 comma 3, 1 comma 3 belongs to R and 3 comma 9 belongs to R, implies 1 comma 9 does not belongs to R. See, 1 comma 3 is there, 3 comma 9 is there, 1 comma 9 does not belongs to R. So, therefore, R is not a transitive. So, therefore, what do you say? R is not equivalence relation. Equivalence relation. So, if you do this much, definitely you will get 7 or 8 marks. Okay. So, R is not an equivalence relation. Okay. Now, let us take a similar type problem. Let me explain one more problem. A relation R in the set n of natural numbers defined as R is equal to x comma y such that y is equal to x plus 5 and x is less than 4. Check whether R is an equivalence relation or not. What is the given condition? X comma y, x, and what is y? X plus 5. And the elements are less than 4. Less than 4 means 1, 2 and 3. Now, therefore, the relation R is equal to, when x is equal to 1, y is equal to x plus 4 means 1 plus 4, that is equal to 5. When x is equal to 2, y is equal to 2 plus 4, 6. When x is equal to 3, y is equal to 3 plus 4, it is 7. So, therefore, the elements of the set R are, the relation R are, when x is equal to 1, y is equal to 5. When x is equal to 2, y is 6. When x is 3, y is 7. So, these are the elements of R. Now, check one by one. First one, reflexive. Reflexive. So, here R is not reflexive. R is not reflexive. What is the reason? Because A comma A does not belongs to R. That is 1 comma 1, 2 comma 2, 3 comma 3 does not belong. So, R is not reflexive. Next, symmetric. Symmetric. So, R is not symmetric. R is not symmetric. The reason is because, let us take 1 comma 5 belongs to R. 1 comma 5 is there, but 5 comma 1 does not belongs to R. Does not belongs to R. So, therefore, R is not a symmetric. And the third one, transitive. Transitive. R is not transitive. R is not transitive because what is the reason here? So A comma B belongs to R and B comma C belongs to R implies A comma C does not belongs to R. So therefore this is not a equivalence relation. Therefore R is not an equivalence relation. So that's it. This is also an example for a not an equivalence relation. Okay. Now let us take one more problem. Now this is also very important. A relation R in the set Z of integers defined as R is equal to x comma y such that x minus y is an integer. Check whether R is an equivalence or not. Equivalence relation or not. What is given? So on R, on the set of real numbers, x minus y is an integer. So integers means I is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are the set of integers. So on these integers, if we subtract any two integers, so x minus y definitely will get an integer. So definitely we can say that this is an example for an equivalence relation. Now let us verify one by one. First, reflexive. Now let us explain this. Now verify just whether the relation is reflexive, symmetric or transitive. Now first one, reflexive. Now, so R is equal to x comma y such that x minus y is an integer. So verify for R is equal to reflexive. Let us take a comma a or x comma x, y comma y, z comma z. So let us take for x belongs to z, x comma x belongs to R, because x minus x is equal to 0. 0 is also an integer. 0 belongs to I. 0 is also an integer. So therefore R is reflexive. That means x comma x belongs to R, x minus x is 0, 0 belongs to R, therefore R is reflexive. Now next one is the symmetric. The second one is symmetric. So symmetric. Now let us consider for x comma y belongs to z or I. If x comma y belongs to R, then x minus y is an integer, means y minus x is also an integer. X minus y is an integer means x minus y is an integer, which implies y minus x is also an integer. Y minus x is also an integer. That means if x comma y belongs to R, implies y comma x also belongs to R. Right. Suppose if take for example, if a is equal to 2, b is equal to 3, 2 minus 3 is equal to minus 3 is minus 1, belongs to an I integer. Again 3 minus 2 is also equal to 1, which also belongs to an integer. So that means if a come 2 minus 3 implies 3 minus 2 belongs to R set of integers. So therefore it is symmetric. R is symmetric. That is, for every x comma y belongs to z or I, x minus y is an integer, means that means x minus y is an integer implies y minus x is also an integer. So if x comma y belongs to R, implies y comma x also belongs to R. So therefore R is symmetric. Now let us come to the third one. Third one is the transitive property. Transitive. What is transitive? If x comma y and y comma z belongs to R, for all x, y, z belongs to z, that is, if x minus y and y minus z are integer, if x minus y is an integer and y minus z is an integer, implies x minus y is equal to x minus y plus y minus z, that is x minus y plus y minus z. X minus y plus y minus z, I will write like this, x minus y plus y minus z. So plus y minus y gets cancelled, this is equal to x minus z belongs to R. That means, so therefore R is a transitive. So R is also transitive. So that means if x comma y belongs to R and y comma z belongs to R, implies x comma z also belongs to R. Therefore R is a transitive. That means, so R is reflexive, symmetric and transitive. Hence R is an equivalence relation. R is an equivalence relation. So here x minus y plus y minus z, that's equal to minus y plus y gets cancelled. You will get x minus z. So x minus z, therefore x comma y belongs to R and y comma z belongs to R implies x comma z also belongs to R, therefore it is transitive. Hence it is an example for equivalence relation. Now move on to the next one. Show that the relation R defined by R is equal to A comma B such that A is less than or equal to B is reflexive and transitive but not symmetric. Now let us write the solution. What is given? The relation R is equal to A comma B such that A is less than or equal to B. Now let us take first one, reflexive. Reflexive. What is reflexive? For all A comma A belongs to R implies A is less than or equal to A. Yes, A is equal to A. So therefore R is reflexive. A is less than or equal to A implies A is equal to A here. That means R is reflexive. Now second one. So let us take for example, if reflexive. Second one is symmetric. 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 What is symmetric property? If A comma B belongs to R, A comma B belongs to R implies B comma A also belongs to R. Now let us take an example. If 2 comma 4 belongs to R, if 2 comma 4 belongs to R implies 2 is less than 4. This is true. Next, B comma A means 4 comma 2 belongs to R implies 4 is not less than 2. 4 is not less than 2. So 4 is greater than 2. See, 2 comma 4 belongs to R as 2 is less than 4, whereas 4 comma 2 implies 4 is not less than 2. So 4 is not less than 2. So therefore this does not belongs to R. So therefore R is not symmetric. R is not symmetric. Right. Now last, transitive. The third property, transitive. Transitive. What is transitive? If A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. So if A is less than or equal to B, say A is less than or equal to B and B is less than or equal to C implies A is also less than or equal to C. Let us take an example. If A is less than or equal to B and B is less than or equal to C implies A is also less than or equal to A is also less than or equal to C, that is A comma C belongs to R. So R is transitive. Now let us take a small example for this. 2 comma 2 is less than 3 and 3 is less than 4 implies 2 comma 4, that is 2 is less than 3 and 3 is less than 4 implies 2 is also less than 4, right? So 2 is less than 3 and 3 is less than 4 implies 2 is also less than 4. So therefore R is transitive. Now what is say from this? R is reflexive, whereas R is not symmetric. R is reflexive, not symmetric, but it is transitive. So therefore what you say? Therefore R is reflexive and transitive but not symmetric. R is reflexive. R is reflexive and transitive. R will satisfy reflexive and transitive but not symmetric. But not symmetric. Right, but not symmetric. So this is how we are going to verify the given problem. So this is how we are going to verify the reflexive, symmetric and transitive, that is an equivalence relation. These are all very, very important concepts. So in the examination they may ask what is a relation and write different types of relation with an example. What is a function and different types of function and the problems based on this reflexive relation, symmetric relation and a transitive relation. So you will get one full question from this concept. Hope you followed. So that's all regarding today's session. Let us meet with a different concept in the next session. Thank you. Thank you very much.